Professor Elliott, and in this lesson we will look at the 74LS76 JK binary flip-flop counters. Boy, that was a mouthful. Okay. All right. So let's. Sorry. Okay. So this is some excerpts from the data sheet, just highlighting a few key things that I think you should know. Okay, so first of all, okay, this is the part number. This is the description, which means there's two JK flip-flops in the one package. Okay, so there's the packaging. These are the through hole, which will go into a circuit board and be soldered. Surface mount, you're going to be using these. Okay, okay, so note the truth table. Okay, so this is going to be the same operation that we've discussed in class, and I've also have explained on another video. Note the truth table, which explains how it works. Okay, so the manufacturer is always going to give you a truth table, sometimes called a function table, to explain how the device works. Okay, internal diagram. Okay, note the power supply connections, okay, are not on pins 14 and 7 as per normal. Okay, so notice that okay, so the power is on pin 5 and 13. Okay, for the one JK flip-flop, here's the pins. Here's the other JK flip-flop. Here's the pins. If you're really excited, here's the internal wiring. Okay. Okay, up counter, mod 8, which is going to count 0 to 7. Okay, resets on 8. So it always resets on the mod number, as per usual. All right. Okay, so here is our circuit. For mod 8, we need 3 bits. Normally, you'll see in class, I bring the clock signal, which goes into the least significant bit, or sometimes they call it the least significant digit, same thing, on the right side, because that matches the binary, the way the binary truth table, the binary system works. In the program, I did this in Multisim, which is actually it's a very nice schematic editor circuit simulator. You can get it online. Last time I bought it, it was something like $50, and it was created by a company in Toronto called Electronics Workbench, which later, I believe, sold it to National Instruments. So, which is an American-owned company. So I don't know if the product's based in Canada or the U.S. I don't know how these things go. Anyway, it's the student version is $50 or $60. You can find it online, or if you're interested, tell me. I can point you to the website. But anyway, this is how it shows the JK flip-flops. It has the clock input on the left, and I can't flip it. At least in the version I have, doesn't allow me to do that. So anyway, the clock's on the left, but in class I'll show it on the right. I just think it's a little better that way, but does it matter? No, not really. Okay, because we're using all 3 bits to its maximum capacity, we're tying the reset inputs to their active low are all tied high to 5 volts to disable them. The set PR stands for preset. So PR equals preset, which equals set, okay, which should be tied to logic 1 if unused. Okay? All right. Waveforms. Okay, so you can see the full waveforms. So we see the clock, we see Q0, the LSB, Q1, and Q2. And I put the whole count sequence in here. So it goes 0, 1, 2, 3, 4, 5, 6, 7, temporarily goes to 8, right here where that line is, okay, which clears the flip-flop, automatically just rolls over, and then we start the next cycle. Okay, so, all right, so please study these until they make sense, okay? And then I'll ask you, can you draw these on? All right, give you a little homework there. 7-segment display. If you're using the displays on the trainer in the labs, they have these decoders drivers in there, which just really translates the BCD, binary coded decimal input here. This is coming from the counter into something the 7-segment display can understand. So basically, then for every binary number here, it will activate, notice they're active low, okay, activate the appropriate outputs to illuminate the correct segments on the display. So, and these are just resistors are for current limiting. So these are all built in on the trainer. The caveat I must warn you is that the day that you need them, they may or may not be working. Somebody could have damaged them, put the wrong voltage in, and that. So I think you're pretty safe, but I'm not going to 100% guarantee that they're going to be working. Hopefully they are. If you're wanting to, and some students always do, you go down and you buy the decoder chip, buy the display. Make sure it's a common anode display there. If you're going to use this part number, or it won't work together, to wire the display on your own. Okay. Now that might be worth a few extra bonus marks. You're not going to get the full amount. Okay, because this is not that complicated. And most of your professors were wiring this in high school. Okay, so it's worth a little bit extra, but it's not overly impressive. But it's a good exercise for you anyway. But so I'll leave it up to you. Okay. Okay, so that just summarizes a little bit about what I just talked about the display circuitry. So pause here so you can digest that before going on. Okay, if you're using the Logic Trainer display, here's the connections. Okay, so take a screenshot, write this down, whatever's easiest, most efficient for you. Okay, I'm not going to say anymore. Mod 10 counts 0 to 9. Again, with the 7-segment display. So each digit can only go 0 to 9. Resets on 10, so that's your mod 10. So this is a mod 10 counter. Okay, mod 10, then we have to reset on 10, and at the count of 10, outputs Q1, Q1, and three are both high at the same time. So when that happens, so basically it counts 0 to 9. On 10, Q3 is 1, Q1 is 1. That triggers the reset circuitry with the AND gate, flashes the clear is low, the output then rolls back to 0. So we need to prematurely reset the counter because we have 4 bits. If we just left it on its own, it would give us a mod 16. We wanted a mod 10, so we have to add this gate circuitry in. And again, the counter outputs feed down to the display. Okay. Okay, mod 20 counts 0 to 19, 7-segment display. Okay, so I'm going to let you look at that. I'm just going to say just a couple little things. Okay, so write that down, take a screenshot, whatever's most efficient for you. Okay, so we have a mod 10 section. Okay, so when you're using the 7-segment display, the right-hand display, the least significant display, must be a mod 10. Okay, so, and then the other section is mod 2, mod 10 times mod 2. So mod 10 times mod 2 equals mod 20 overall. Okay, and each counter section interfaces with its own decoder driver, which if you're going to do this manually, you're just follow this. And you can easily change the mod number to something else. Okay, and if you're using the displays on the trainer, again, hopefully they're working, then you can just plug the outputs directly in because this is all internal. Okay, so look at that carefully. Make sure you understand it. If you don't, come see somebody for help, which might be me. Okay. Rising edge clock. Okay, so everything we're doing in class for the most part is the falling edge clock flip-flops because that's what we have. They're all rising edges available. Now this diagram here is it shows you can see here the outputs. This is the rising edge, so it's a rising edge. Okay, these are the propagation delays. So these are the propagation delays, or how long it takes the change at the clock to propagate through all the internal transistors to appear at the respective outputs. And they've exaggerated it here, but this is a data sheet value, okay? And the faster you clock it, right, you eventually will hit a point where you're clocking the input so quickly the output falls out of sync, which of course is going to be a problem. Anyway, so whether it's rising edge or falling edge activated, so that'd be the falling edge, this is rising edge, the propagation delays are there. Anything we're doing in this course, it's a non-issue, but in the real world, they are there and they often need to be considered. Okay. Okay. Okay, so let's just put real life applications may need to consider the flip-flop propagation delays. Good. Okay, here's the circuit. No bubble on the inputs. That's how we know the rising edge. Okay, you can see it's triggered on the rising edge. There's the waveforms. Okay. Can you notice the connection differences? Okay, how are the flops of a rising edge clock connected? Okay, we carry forward the not Qs. If it's falling edge, we carry forward the Qs. Okay, so compare with the falling edge counter circuits. All right. Down counters, mod 8, it's going to count 7, 6, 5, 4, 3, and down to 0, and then back to 7. Okay. Okay. So notice the connections. Okay. I've brought forward the not cues to make this into a down counter. Okay. So I've explained you can also do it this way as well. Okay. So just note the connections. All right. In case they show up somewhere in a test or something. Waveforms. Okay. Clock. Q0, Q1, Q2. Count 7, 6, 5, 4, 3, 2, 1, 0. Resets. Naturally, it goes back to 7 because we have a natural rollover because all bits are being used. So we don't need to do anything funny with the at the reset state. Okay, so be sure you're familiar with that. Okay. 7-segment display. The connections here are exactly the same as before. Okay. The counter outputs come down to here. So this is all the same, right? And this is the actual counter. Okay. So, yeah. So I guess that's about it. I hope it was beneficial to you, and they got a little bit out of it. All right. And yeah. Oh, sorry. I just thought I missed something there. No, I'm okay. We're okay. We're all done. Okay. All right. Thanks for spending time with me looking at the video. All right. Cheers. Bye bye.